இந்த வீடியோட தமிழ் வெர்ஷன் கமெண்ட்ல பின் பண்ணிருக்கேன். Make use of it. In this video, we will go through the answers for part A questions from BE3251 Basic Electrical and Electronics Engineering, April-May 2022 question paper. Look at the first question. In this question, we need to determine the current in a circuit. Let's look at the circuit. We have a 36 volt battery connected in series with three components, a 15 ohm resistor, a 7 ohm resistor, and a dependent voltage source marked as 2 VA. Now VA is voltage across 7 ohm resistor. Since voltage across a resistor equals current times resistance, that is, voltage across a resistor is equal to current multiplied by resistance. This is the basic formula for voltage, which is V equals I into R. V is voltage, I is current, and R is resistance. In 7 ohm resistor, resistance is 7 ohm, current is I. So voltage across is I into 7, or simply 7I. Now dependent voltage source is 2 times VA. Since VA is 7I, we multiply 2 times 7I, that gives us 14I watts. Now apply Kirchhoff's voltage law around the loop. That is, total supplied voltage equals total voltage drop in the loop. So when we apply Kirchhoff's voltage law, whatever voltage the battery gives, it will be completely used up as a voltage drop across the resistors and the other components. Therefore, whatever the battery gives, the circuit uses. That's why supplied voltage equals total drop. Now write the equation based on the voltage drops in the loop. 36 equals 15I plus 14I plus 7I. Now let's simplify that. 15 plus 14 plus 7 is 36. So it becomes 36 equals 36I. Now solving for current, we divide both sides by 36. So I equals 36 divided by 36, which gives us I equals 1 ampere. So the current flowing in the circuit is exactly 1 ampere. Second question is, write down the expression for active power and apparent power. First, active power. It is also called as real power. Active power is a power actually consumed by the load to do useful work, like running a fan or lighting a bulb. It is given by the formula P equals V into I into cos theta, where P is active power. This is the actual power used by the circuit to do work. It is measured in watts. V is voltage in volt. I is current in ampere. Cos theta is power factor. It tells us how much of the supplied power is actually being used. Theta is the angle between voltage and current. Next, apparent power. It is the total power supplied by the source, whether it is used or not. It is given by the formula S equals V into I, and it is measured in volt amperes or VA. In this, S is apparent power, that is total power supplied by the source. V is voltage in volt. This is electrical pressure that pushes current through the circuit. I is current in amperes. This is the flow of electric charge through the circuit. Look at the third question. A 6-pole lap-wound DC generator has 720 conductors. The flux per pole is 40 milliwebers. The machine is running at 400 revolutions per minute. Now find the generated electromotive force or EMF. To solve this problem, we use EMF equation of DC generator. And the formula is E equals P into 5 into Z into N divided by 60 into A. Here E is generated EMF in volt. P is number of poles, which is 6. Phi is flux per pole. It is given as 40 milliwebers. That is 40 into 10 to the power of minus 3 webers. Z is total number of armature conductors, which is 720. N is speed, which is 400 RPM. And A is number of parallel paths. Since the machine is lap wound, we know that number of parallel paths A is equal to number of poles P. So A is equal to P. Therefore A is 6. Now substitute the values in formula. Notice 6 in numerator and denominator cancels out. Now calculate the numerator. Multiply 0.04 with 720, which gives 28.8. Now multiply this with 400, which gives 11,520. Now divide this by 60, so that we get 192 watts. Therefore, the generated EMF of 6-pole lap-wound DC generator is 192 watts. Now fourth question, list out the applications of transformers. Transformers have several important applications. First, they are used for voltage step up and step down in power systems, which helps in efficient power transmission and safe distribution. Second, transformers provide electrical isolation between circuits, thereby it protect equipment and ensure safety. Thirdly, they perform impedance matching in electronic and communication systems to maximize power transfer. Finally, transformers play a key role in power distribution and transmission, which enable electricity to reach homes and industries at the right voltage levels. It is also used inside small electronic devices like mobile chargers, adapters, and laptop chargers. Fifth question is, name the 4 regions of operation of transistor. First, cutoff region. In this region, the transistor is off. Both the base emitter and base collector junctions are reverse biased. Because of this, no current flows through the collector except a tiny leakage current. The transistor acts like an open switch. It doesn't allow current to pass from collector to emitter. In short, cutoff region means the transistor is off and it behaves like an open switch, so no current flow. Next, active region. In this region, the transistor is on but not fully. The base emitter junction is forward biased. The base collector junction is reverse biased. The transistor works as an amplifier. It takes a small base current and controls a larger collector current. That is, the collector current is controlled by the base current. This is the normal operating mode for amplifiers and other linear applications. So active region means the transistor is on and is used to amplify signals. With small input, it controls big output. Next, saturation region. In this region, the transistor is fully on. Both the base emitter and base collector junctions are forward biased. This allows maximum current to flow from collector to emitter. The transistor behaves like a closed switch, almost a short circuit between collector and emitter. The voltage between collector and emitter is very low, typically around 0.2 volt. In short, saturation region means transistor is fully on and it lets maximum current pass just like a closed switch. Next, breakdown region. In this region, the collector base junction is reverse biased, but the voltage becomes too high and thus it exceeds the critical limit called breakdown voltage. When this happens, the junction breaks down and a larger current suddenly flows. This can overheat and damage the transistor permanently. So it is an unsafe region and is usually avoided in practical circuits. In short, breakdown region is a danger zone because too much voltage causes uncontrolled current and the transistor can burn out. Sixth question is, differentiate the operations of rectifiers and inverters. Let's begin with a real life scenario. At home, we get electricity in form of AC, that is alternating current, but many electronic devices like phones and laptops need DC to work, that is direct current to work. To convert AC to DC, we use a rectifier. Now imagine we have a battery like in a solar panel or UPS system. Batteries give DC power, but most appliances like fan and TV need AC power. To convert DC to AC, we use an inverter. So the main function of rectifier is it changes AC to DC. It takes current from the wall and gives smooth current for devices, whereas inverter changes DC to AC. It takes battery power and makes it like a wall current. Next, input type. Rectifier input is AC. It gets current from plug point, whereas inverter input is DC. It gets power from battery or solar. Next, output type. Rectifier output is DC. It gives steady current like what phones need, whereas inverter output is AC. It gives wavy current like what fan and TV use. In short, a rectifier is like a filter. It straightens the back and forth flow into one direction, that is DC. An inverter is like a wave machine. It takes steady DC and turns it into back and forth AC. So think of AC as water moving back and forth in a pipe, and DC is water flowing in one direction only. Next, example. Example for rectifier is phone charger. Your charger has a rectifier inside. An example of inverter is home UPS. When power goes, inverter gives backup current. Next, types. There are different rectifier types like half wave and full wave, and it is about how they change AC to DC. Inverters have types like sine wave, square wave, and modified sine wave, after which current flow. In rectifier, current flows in one way. like a straight road, whereas in inverter, current changes the direction periodically, like a swing. Seventh question is, convert the given expression in canonical SOP form. The given expression is y equals AC plus AB plus BC. Let's convert the Boolean expression into canonical SOP form. In this form, every term must include all variables, either in normal or complemented form. Now we want to expand each term to include all variables. Expand AC. We want to include B in the term AC. We can use the identity B plus B dash equals 1. First we multiply AC by B plus B dash. Since B plus B dash equals 1, we haven't changed the value of AC. So we distribute AC across B plus B dash. This gives us AB dash C plus ABC. And you can see the two terms includes all three variables. Next, the second term AB. Here C is missing. To include C, we again use the identity C plus C dash equals 1. So we can rewrite AB as AB into C plus C dash. Just like before, since C plus C dash equals 1, we haven't changed the value of AB. Now we distribute AB across C plus C dash. This gives us ABC plus ABC dash. Finally, expand the third term BC. Here the missing variable is A. To include A, we use the identity A plus A dash equals 1. We rewrite BC as BC into A plus A dash. Since A plus A dash equals 1, we haven't changed the value of BC. So distribute BC across A plus A dash. And this gives us ABC plus A dash BC. Now combine all the expanded terms we have created. So the full expression becomes y equals AB dash C plus ABC dash plus ABC plus A dash BC. And remember, we can remove duplicates to get the final canonical SOP form. Eighth question is, mention the significance of K-map. First, it simplifies Boolean expression. K-map helps to reduce complex Boolean expressions into simpler forms by grouping adjacent ones and zeros. Also, it reduces number of logic gates. So by simplifying the expression, fewer gates are needed. Thereby, it reduces the circuit size. After which, it minimizes circuit complexity, meaning it leads to simpler and more efficient digital circuits. And it is useful for digital logic design, meaning K-map is widely used in designing optimized circuits for computers and electronics. And ninth question is, name the constructional parts of induction type energy meter. An induction type energy meter is a device that measures the energy consumption in our homes. It uses the principle of electromagnetic induction, which means it uses magnetic field to measure how much electricity we are using. Let's break down its main parts. First, driving system. It is like engine of the meter. It consists of two magnets, shunt magnet and series magnet. These two magnets work together to create magnetic field. And this will drive the next part of the meter. Shunt magnet measures the current. Series magnet measures the voltage. Next, moving system. Here is where the action happens. It's a metallic aluminum disc that rotates when it comes in contact with magnetic field. The speed of this rotating disc tells us how much energy is being used. So faster the disc rotates, the more energy is consumed. Then we have braking system. There is a permanent magnet that slows down the rotating disc. And this ensures the disc doesn't rotate too fast. Otherwise, it will lead to inaccurate energy reading. Therefore, the permanent magnet controls the speed to give us the correct reading. Finally, the registering system. It is the part that shows the result. You will see gears and dials here. These gears are connected to rotating disc and thus the disc turns, so it moves the gears, which in turn moves the dials. And these dials display the energy consumed in kilowatt hours. So when you look at it, you will know how much electricity you have used. In short, the driving system creates the magnetic field. The moving system has the rotating disc that shows energy usage. The braking system makes sure the disc doesn't spin too fast. The registering system gives us the reading in kilowatt hour. Tenth question is, how are the errors caused in potential transformers? Errors in potential transformers are mainly caused due to imperfections in their magnetic and electrical properties. These errors affect the accuracy of voltage measurement and occur due to following reasons. These are the causes of errors in PTs. First, magnetic losses. Core losses cause ratio and phase angle errors due to imperfect magnetic coupling between primary and secondary windings. Next, imperfect turn ratio. If the number of turns is not exactly proportional, it causes ratio error. After that, burden on secondary. High load connected to secondary affects the voltage and introduces both ratio and phase angle errors. Finally, leakage reactance and resistance. These internal properties in the winding cause voltage drop and phase shift, which lead to errors.